Rahman Rahim. Thanks to Allah subhanahu wa ta'ala for all His blessings and bounties that He has bestowed upon us. فَبِأَيِّ آلَاءِ رَبِّكُمَا تُكَذِّبَانِ. Which of the blessings of your Lord will you both jinn and insan deny? Whatever we see, whatever we can't see, whatever is beyond our comprehension, directly or indirectly, Allah subhanahu wa ta'ala has created everything for the services of the mankind. What we have been created for. Allah subhanahu wa ta'ala says in the Holy Quran, وَمَا خَلَقْتُ الْجِنَّ وَالْإِنسَ إِلَّا لِيَعْبُدُونَ. More or less meaning, I have created the mankind and the jinn only for my worship. Now, how to worship Allah subhanahu wa ta'ala? He's been very, very kind, very, very merciful by sending Nabi alayhi Islam to guide the humanity so that each and every mankind will be successful, not only this life, but the life hereafter. So very simple, very elegant way to get the success of this life and the life hereafter is to follow the commandments of Allah subhanahu wa ta'ala, the way shown by the Prophet sallallahu alaihi wasallam. So inshallah, learning, talking and propagating it will be very, very beneficial for all of us. Today is our fourth lecture of this series of online lectures. So if you remember from the previous lectures, we started off talking about the idea of differential equations, vital properties, why and where we do utilize them, different types of differential equations, and then initially we discussed first order differential equations, their different types, and how do we come up with the solution of those differential equations. Of course, there are quite a few other types available in the literature, but we discussed most common, most vital, being utilized in the literature among the first order differential equations. And then we discussed higher order differential equations. Started off with the idea of higher order differential equations. So remember the difference between the first order and the higher order differential equation is that any differential equation having order greater than 1 is going to be considered as higher order differential equation. Any differential equation with order at least 2 is going to be considered as higher order differential equation. Many of the common terminologies are being utilized for first order differential equations as well as for higher order differential equations. Like linear. When we talk about the first order differential equation, linear has got a different meaning. Like homogeneous and non-homogeneous. When we talk about the first order, has got entirely different meaning in comparison of higher order differential equations. So anyway, we need to keep an eye on those common terminologies being utilized in both cases for first order and higher order. We started off with the idea of higher order differential equation, and we derived the criterion for the solution of higher order differential equations, both homogeneous and for non-homogeneous cases. So we have seen that when we talk about higher order differential equation, we need to introduce some notation over there. And the notation is known as differential operator. Capital D stands for that. And then from there, we look into the auxiliary equation. From the corresponding auxiliary equation, we look into the nature of the roots so that we finally get down with the solution. And when we talk about the non-homogeneous differential equation, in the case of higher order equations, so we have quite a few techniques available. Your mic off, please. Let me. Thanks. All right, for the case of non-homogeneous higher order differential equation, we discussed a couple of vital techniques being utilized in the literature known as undetermined coefficients method, where we take as granted the particular integral, another solution of the given non-homogeneous differential equation apart from the solution of homogeneous differential equation. Yes, if there is an internet problem, so you will get the video link afterwards. Yes, I can expect that distortion would be there. I mean, depends upon the quality of the internet at different places. So recording is there. I mean, it's available. Afterwards, you can get it. Right. So one of the technique available for higher order differential equation is the undetermined coefficients method, the most simplest one. Because what we do for yp, the particular integral of the non-homogeneous differential equation, we take as granted yp an expression from the provided table. And for the second technique, variation of parameters, we look into the variation in the parameters by replacing those arbitrary constants depend upon the order of the differential equation. We look into the calculation of those unknown functions. Okay, I will do that. I mean, it is requested that the video will not be played on MS Teams, so please upload it on YouTube somewhere else. Okay, I will look into that. As we discussed earlier, I mean, this is not the, of course, the ideal case behind the chain. We discussed yes, it's there, we will look into that. We will look into that. It's not the ideal scenario, of course, but we have to cope up with the available resources. Anyway, so the second option was there when we talk about the variation of parameters technique. We calculate basically the unknown functions of x, and then eventually we calculate yp. Today we are going to about a new option, different from the undetermined coefficients, entirely different from the variation of parameters. This technique is known as series solution of differential equations. Many technical terms are being utilized, so try to note down. Still, some of the participants have the microphone on. So if you could turn off your microphone, please. Sure. Okay. 172. If you could turn off your microphone, your screen, please. (172). Please turn off your microphone, your camera.
Okay, sir.
Are you attending for the very first time? All right, so we are going to talk about entirely different technique. Series solution. We are all familiar about the series. The Taylor series is the backbone of applied mathematics, the most famous. Mclaren series is the offshoot of Taylor series. So pretty much on the same line, we will talk about a series solution of differential equations. If you look into the description, in many cases, the solutions of linear differential equations with variable coefficients cannot be obtained in the closed form. So far, we have they are all with constant coefficients. The coefficient of y dependent variable, its derivatives, they were all constant coefficients. But now we are going to talk about a linear differential equation with variable coefficients. If we do have this particular scenario, this particular mathematical formulation of physical phenomena, so we are interested to find its solution by utilizing power series method behind the scene. Another technical term is being utilized, closed form of the solution. What the closed form is? Basically, a closed form solution is a general solution to a problem in the form of closed form expression. What does this mean? It means that we must have finite combination of familiar functions. We must have finite combination of finite combination of binary operations. So with the finite combination of either the operations or the functions known from calculus, we say that the solution is going to be closed form. So as an example, if you look into the previous lecture, so this is the point where we ended up. So how many terms are there? 1, 2, 3, 4. 4 of the terms are there, finite. How many operations are there? Binary operation, addition is there. Or you could also say that multiplication is there in case. So there are also binary operations. So if we have a combination of finite expressions using known functions from calculus together with binary operations, we say that the solution is going to be closed form. And normally what happens when we talk about the series, it will be having infinitely many terms. So when we talk about this series solution, we are not expecting to have a closed form of the solution because we will not be having finite combination of family of functions together with binary operations. Exception is there. The extended version of this definition, the closed form expressions and solutions are typically restricted to certain operations. What are those? The binary operations. Addition, multiplication, subtraction, and division. And normally,
सर ये आप किसी की वॉइस ऑन है तो जिसकी वजह से आवाज सही नहीं आ रही है आपकी.
let me double check. I requested over and over again. Okay, everyone is muted now. Thanks. All right, we were talking about the closed form. So normally what happens, if the solution is having infinitely many terms, infinite combination of functions like exponents, logarithmic, trigonometric, and inverse trigonometric functions together with binary operation, we say that it is not going to be closed form. Yes, the finite combination of functions and operations is going to be closed form of the solution. As a remark, limits and other operations that involve an infinite number of terms or operations are not going to be permitted, because if they do involve, again, it is not going to. So many of the most important differential equations in applied mathematics, for example, Bessel's, Legender's, hypergeometric equations are of this type. I mean, of what type? We are looking for the solution. Such type. Since these type of equations and their solutions, they play a vital role in applied mathematics, so we are going to consider one of the standard method known as power series method, which yields solutions in the form of power series. And we know what the power series is. From the assumed knowledge from calculus, we know that a power series in powers of x minus x naught is an infinite series of this particular form, a naught, x minus x naught raised to power 0, and we know that it will turn out to be 1. So this is all we have a naught. Otherwise, it is of course multiple of x minus x naught, as you see in the second term. So the subscript of a and the power of this expression, they are compatible with each other. Over here, basically, we have x minus x naught raised to power 0 compatible with the subscript of this unknown constant a. In the second term, a1, x minus x naught raised to power 1. Third term will involve a2. So compatible with that power or with that subscript, and so on. So on means pretty much on the same line, we can extend our journey. So the next term would be a3, x minus x naught raised to power 3, and so on. And we know about the difference between sequence and series. So series is the combination of the terms. Sequence is a systematical arrangement of terms. And when we combine together the terms of a sequence, it will turn out to be a series. So it's very systematical arrangement, like you see that. There is a compatibility between the power of this factor x minus x naught and the subscript of unknown constant over there. If you combine together, the most precise form in the summation notation, it would be a kx minus x naught raised to power k, where k is going to be non-negative integer. And we know that non-negative integer starts off with 0, 1, 2, 3, and then so on. And finally, many terms are there. So this is how we have the upper limit being infinity. What are those? A0, A1, A2, A3, and so on. They are all constants known as coefficients of the series. AK, the most vital term of this series, is known as the kth term because we have utilized the k being the subscript, otherwise it would have been nth term if you do utilize an. So it is known as center of the series. The x naught is going to be the center of the series, fixed value, constant value, and then x is known as variable. If in particular x naught is 0, I mean the center is 0, then we obtain a power series in the powers of x as plug in x naught equal to 0 everywhere, and we have an expression of this nature: a naught plus a1 x raised to power 1, a2 x raised to power 2, plus a3 x raised to power 3, and then so on. Now, if you look into this expression, for an example, a naught plus a1x plus a2x here, what is this? So pretty much like a quadratic polynomial, axk plus bx plus c, alternatively, with different constants, coefficients. So it means that this expression is also a polynomial. The power series expression is basically polynomial behind the scene because they have this particular form. So vital note is there. Polynomials are also power series. Why so? Because they have this particular form. We look into the examples. Few of the examples are there from the literature. Well-known examples are there. They are known as Mclaren series. When x naught is going to be 0, explicitly, so we will be having Mclaren series. 1 plus x k plus x cube. So it's a geometric series, and we know the property behind the scene for a geometric series. Mod of x should be less than 1. Provided that the geometric series is going to be convergent. E raised to power x, another famous expression for exponential function, e raised to power x. So the series is there: 1 plus x here upon 2 factorial, x cube upon 3 factorial, and then so on. Combined as one unit, the most compact and composed form, representing in terms of kth term, sine of x. A trigonometric function is there, which is equivalent to this series: x minus x cube upon 3 factorial plus x5 upon 5 factorial minus x raised to power 7 upon 7 factorial plus so on. So you see that there is an alternative sign: plus minus plus minus plus minus, and then so on. So this is how we adjust the negative sign: minus 1 raised to power k, an additional factor. With k starts off with 0, so minus 1 raised to power k, if it is replaced by 0, means 1. So 1 means positive sign, and then if it is 1, you carry negative sign, and then so on. So these are few of the examples. You see that a power series is there in the powers of x with infinitely many terms every time. Infinitely many terms, infinitely many terms, infinitely many terms are there. Another definition before we move on with the technique, ordinary and singular points of a differential equation. Since we are going to talk about a special type of the differential equations with variable coefficients instead of constant coefficients. So here you go. Take an example of a second order linear homogeneous differential equation with variable coefficients. So a naught of x, the coefficient of y double prime is going to be function of the variable x, coefficient of y prime, as well as coefficient of y. Y is going to be dependent variable, whereas x is going to be independent variable. So coefficients are going to be functions of the independent variable. So this is how we describe it. Homogeneous because of the right hand side is 0. It's a second order because the highest derivative that appears in this equation is order 2. Double prime stands for second order. Second order, linear. Yes, we know the property. Homogeneous. Yes, we know because the right hand side. With variable coefficients. Yes, because of the coefficients of the dependent variable and its derivatives are going to be function of the variable x. Provided that as a precautionary measure, a naught of x can't be 0. Because if you take it equal to 0, surely the first term is going to be vanished. And if there is no first term to the left hand side, the extreme left term, if it is vanished, the order of this equation won't be 2, can't be second order. It is only because of this, the second derivative is there. So surely the coefficient of the second derivative should be non-zero in order to have this equation to be second order. So what we do? We divide by the coefficient of the second derivative on both sides. So what we do? We will be having a1 upon a naught. We will be having a2 upon a naught. We label this fraction by p and the fraction over there once we divide it by a naught, so by q, capital Q. What is p? Stands for the fraction between a1 and a naught. And q stands for the fraction between a2 and a naught. 1 second, please. Excuse me. Yes, please. So we write it down, the fraction being the coefficient of y prime as capital B, the fraction being the coefficient of y as q. So we have very precise form. Y double prime plus p of x times y prime plus q of x times y equal to 0. We assume that let x naught be a point in some open interval capital I as an arbitrary interval. So this point x naught is said to be ordinary point of this equation if a naught of x naught is non-zero. For this particular value of x, the coefficient of the second derivative is non-zero. First condition. And second condition is that P and Q being functions of x are analytic at x naught. So again, two conditions are there. For x naught to be ordinary point, because we are going to define ordinary and singular points of a differential equation. A point, arbitrary point, is said to be ordinary point if the coefficient of the second derivative for this particular value of x is non-zero. On top of that, the coefficient of y prime and y being functions of x are analytic at x naught. What is analytic? You need to dig more and to get down with the definition of analytic function, because generally we talk about the complex analysis. We talk about the complex numbers behind the scene. For the time being, analytic means a function which is defined and differentiable at a particular point is to be analytic function. So we say that P of x is to be analytic at x naught if it is defined and differentiable at x naught, means having derivative q is to be analytic if it is defined and differentiable at x naught. And we know that when it's going to be undefined, p and q, generally when the denominator is going to be zero. Denominator is going to be zero, because in this way something upon zero is going to be undefined. So we say that p and q, they should be defined and differentiable, and on top of that the coefficient of y double prime should be non-zero in order to have this value x naught to be described as ordinary point. Ordinary point is also known as regular point, whereas a point which is not ordinary point is known as singular point. So x naught is a singular point if the coefficient of y double prime is zero for this particular value of x naught, or if either p or q fails to be analytic at x naught. Analytic means defined, should be defined and differentiable at x naught. Take an example to describe this concept before we move on with the power series method. Find the ordinary and singular points of the following differential equation. So you see that very special type of the differential equation. It's the second order, but with variable coefficients. Coefficient of y is variable, coefficient of y prime is variable, coefficient of y double prime is also variable. So it is homogeneous, second order, but with variable coefficients. We are interested to find ordinary and singular points. Keep an eye on the definition. A point is said to be ordinary if the coefficient of the second derivative is non-zero for this particular value of x, and p and q are analytic, defined and differentiable at that particular value of x. Otherwise, it is going to be singular. So what we do, first of all, we label them. The coefficient of y double prime as a naught, the coefficient of y prime as a1, and coefficient of y as a2. No, when it could be equal to 0, a naught, put it equal to 0 to get down with those certain values of x. We say that when x equal to 0 and x equal to 2. So these are the points at which a naught is 0. So once a naught is 0, it means that the point is going to be singular point. So again, point is said to be ordinary point if a naught is non-zero. If a naught is 0 for that particular value of x, the point is going to be singular point. And we see that by coming around the way, when x is equal to 0, because of this factor, a naught of 0 is 0. And when we take x equal to 2 over here, this factor is 0, means everything is 0, a naught is again 0. For these two values, a naught is 0, so x equal to 0 and x equal to 2 are going to be singular points. Also, when we look into the friction a1 upon a naught, plug in those values for a1, and because of the common factors, x naught is going to cancel out, and we left with this expression a2 upon a naught. So we will be having this expression because x square is going to be cancelled with x square, and we left with 3 upon x times x minus 2 square. So are not analytic. You see that P of x is not analytic when x is equal to 0, because when x equal to 0, P is undefined. Also, when x equal to 2, P is undefined. Same is the case with Q. When x is equal to 0, Q is undefined, as well as when x equal to 2, Q is undefined. So we say that x naught and x2, x is equal to 0 and x equal to 2. At these points, P and Q are not analytic. A naught is 0 for these two values. So we say that x equal to 0 and x equal to 2 are singular points, whereas all other real numbers, other means except 0 and 2, are the ordinary points, of the given differential equation. So this is an idea when we talk about the ordinary and singular points. If the coefficient is 0, the coefficient of the second derivative and P and Q are not analytic, we say that the point is going to be singular, otherwise it is going to be ordinary points. Now we move on with the technique. Power series method. Got an idea about the power series? What the series is? Series in the form of powers of x or a factor x minus x naught. And we know the definition of ordinary point. So keep an eye on those two definitions. We move on with the technique now. It is not going to be very complicated, but you need to be careful when we talk about the solution of a certain type of the problem, because the point has to be ordinary, otherwise you can't move on with the solution of power series. The power series method is the standard basic method for solving linear differential equations when we have coefficients being variable. The power series method is used to seek solutions in the form of power series about an ordinary point. So point has to be ordinary. So when we look into the description, we take start by talking about the second order homogeneous linear differential equation with variable coefficients. Assume the solution of this differential equation in the form of power series n the powers of x minus x naught, or that's what we need to take start. Why? In the power of x minus x naught. So this is the generalized representation. The first term a naught plus a1 x minus x naught raised to power 1, a2 x minus x naught raised to power 2, and then so on. So we take start by looking into the power series in the powers of x minus x naught with unknown coefficients a naught, a1, a2, a3, and then so on. So these are the coefficients to be obtained. How we do that? Since we assume that it's a solution, y is a solution of this differential equation number 19. So we will accept this as a solution when not only y, but also its derivatives, first and second, they satisfy simultaneously equation number 19. And since we assume that y is a solution, so not only the value of y in the form of series, but also its first and second derivatives, they will satisfy this equation. So compute the first and second derivatives of y, differentiate this one with respect to x, because y is a function of x. So in order to yield with an expression for y prime, we differentiate it with respect to x. So here you go, with the first derivative. So when you take the first derivative to the right hand side, this constant term is going to be vanished. From the second term, we are going to differentiate with respect to x, remember. So we left with a1. So this is going to be the starting term. Second term, so derivative to this one, I mean, simple case is there. Take the power sideways, reduce the power by 1, and then further derivative of this expression with respect to x is going to be 1, and then so on. Similarly, differentiate this one twice with respect to x, or once more this one with respect to x to get down with y double prime. So it's y prime of x, basically. Typographical error is a y prime of x. It's a typographical error. It's y double prime of x. So here is the expression of y double prime and y prime. I will make correction in the next lecture. So it's y prime of x, y double prime of x. Anyway, so once more, if you differentiate this one, so first term is going to be vanished. From the second term, we left with 2 times a2, and then so on. The rest of the terms are going to be pretty much on this pattern. The most important point to be noted down, when we talk about y, we will be having infinitely many terms, but the starting value of k is 0. So this is all, you will get a naught. But when we talk about y prime, so we need to take start from k is equal to 1, because one of the term is going to be eliminated. Still, we have infinitely many terms, remember, because if you decrease one term from infinitely many terms, so it won't affect infinity, but yes, the starting point is going to be affected. We take start from k equal to 0, so that we will be having the starting term as a naught, labeled as a naught. But when we talk about the first derivative to this one, k has to take start from 1, still infinitely many terms, but k has to take start from 1. You can also generate it from here. You see that if you take the derivative to this expression to the left hand side, bring the power sideways, and reduce the power by 1. So this is all the power formula is there. Very simple formula is there. And when we differentiate it once more, so it means that one more term is going to be eliminated. And now you need to take start from 2. One more derivative, bring this power as well, sideways, k times k1, k minus 1, times x minus x naught raised to power k minus 2 now. So this term, it is basically corresponding to the third term. A2 involves in the third term to the right hand side of this expression of y. But anyway, once we differentiate it once, first term is going to be eliminated twice, second term is going to be eliminated, and we take start from the third term. So now we have y prime, and y double prime. Everything is there. So plug in those expressions of y prime, y double prime in this equation number 19. And you will be having coefficients of different powers of x. So replace this whole expression of y prime from this equation number 21, y double prime from this equation number 22. So once you plug in all these values of y prime, y double prime in equation number 19 and collect like powers of x minus x naught, then equate the coefficients of each occurring power of x minus x naught to 0. This gives relations from which we can easily determine the unknown coefficients of equation number 20. What are we looking for? A naught, A1, A2, A3, A4, A5, and then so on. So plug in those. Plug in those values for y prime, y double prime. So once we plug in and equate to 0 the coefficients of each occurring powers, we will get those unknown coefficients, A0, A1, A2, A3, and then so on. So plug in those values of those unknown coefficients, A0, A1, A2, A3, and then so on, in this equation. So A0, A1, A2, so plug in those values over there. So once we have those values, so it is going to describe, in this equation, effectively in this equation. So once we plug in those values over here, so it will take us to the solution of the given differential equation number 19 with variable coefficients over there. So there might be a correction again once more. So substitute these coefficients in equation number 1 to obtain in 19. It's basically 20. So to obtain the series solution of the given differential equation number 19. So plug in the coefficients in equation number 20. So two typographical errors are there. One is that symbolic representation, and the second one is that number 20 over here. So it's not that demanding, remember. So what we take start with this assumption. Whatever the form of the equation is there, so you need to take start from here. Depends upon the number of derivatives involved in the equation. You need to take as many derivatives, plug in those derivatives, and find the corresponding values of A0, A1, A2, A3 by equating the coefficients, of like terms of x minus x naught. So in this way, we will find those unknown coefficients. Take an example. We start off with the simplest example. Y double prime plus y equal to 0. It's a second order, homogeneous, linear. You could take as granted the coefficient of y as a function of x. Yes, one could be considered as function of x. Coefficient of y double prime could be considered as function of x as well. And you will see that x naught, x equal to 0 or x naught equal to 0 is going to be ordinary point. Yes, because if you look into the coefficient of y double prime, it's non-zero for this value of x. The fraction is also non-zero for that particular value of x. All the criterions are fulfilled so that we can apply the power series method behind the scene. What the power series method is, we assume a series in the powers of x minus x naught. So remember over here x naught is 0, so it will be in the powers of x. So what we assume? Y as a power series solution of the given differential equation. Remember, because x naught is 0, so once x naught is 0, so our expression of the power series would be of this form. Otherwise, it would have been something like that. Now plug in x naught equal to 0 here, everywhere. So it will turn out to be a naught plus a1x plus a2x squared, a3x cubed, and then so on. Because the center is at 0, so this is all our expression for y as an assumption to be of this nature. We need y double prime as well, so take its first and then second derivative. Since we assume y is a solution, so we need to plug in y and y double prime in this equation. So simplify them, equating the coefficients of various powers of x to 0, we will get a2 minus a naught upon 2. So remember, we can't find certain value for a naught and a1. So what we do, we write it down, all those unknown coefficients, all those constants in terms of A0 and A1. Like A0 is there, A1 is there, but when we look into A2, it is expressed in terms of A0 minus A0 upon 2. Could also be written as minus A0 upon 2 factorial to make a systematical arrangement. A3 minus A1 upon 6 could also be written as A1 upon 3 factorial. A4 is basically A2 upon 12, but we know A2 minus A0 upon 2 factorial. So simplify that. Eventually, we will be having A0 upon 4 factorial, A5 in terms of A1. So A1, and finally, we will be having this expression, A1 upon 5 factorial. A2 is there, minus A0 upon 2 factorial, A3 is there, minus A1 upon 3 factorial, A4, A5. So you see that A0 is unknown, A1 is unknown, they are arbitrary values, and every other coefficient is expressed in terms of either A0 or A1. So substitute the values of A2, A3, A4, A5 in that equation number 23, because this is our assumption for the solution. We get the following series solution. So this is how the series solution will be. A0 is unknown, A1 is unknown, arbitrary values. A2 is expressed in terms of A0, A3 expressed in terms of A1, A4 again expressed in terms of A0, A5 expressed in terms of A1. Double check those expressions. That, I mean, there might be a type of graphical error. Anyway, so if assume that the expression is of this nature, so further we could also simplify that by rearranging the terms, combine those terms with A0, the first, third, fifth. So in this way, second, fourth, sixth, and then so on in that particular fashion. So this is going to be the solution. So you see that it's a series solution. How many terms are there? Infinitely many terms. So this is an example. Again, have a look. Very simple. Assume the solution depends upon the value of the ordinary point. In this case, x is equal to 0. So assume this power series solution, and then depends upon the derivatives involved. Plug in those expressions, simplify that. Our target is to find A0, A1, A2, A3, A4, and then so on. So once we find, plug in all these values over here, so we'll get the corresponding series solution of the given differential equation. Alright, in the next few minutes, try this example. Solve the following differential equation using the power series method about an ordinary point x equal to 0. G. Take an idea what we have to do. So again, x naught is 0. So you need to take start for an expression of y in the powers of x, a0 plus a1x plus a2 xk plus a3 xq, and then so on. You try in the next few minutes. I mark your attendance and also make correction those. Try to make correction to those typographical errors.
Excuse me, sir, please show the slide.
Just a minute, just a minute. I create a new poll for your attendance. So make sure that everybody respond to the online created poll for their attendance. Sometime, of course, distortion is there. Internet issues are there. Anyway, it is going to be created. Yes, it's there. So you need to respond to the created poll for attendance purpose. I had a query. Please share the slides before the lecture. Yes, normally it is uploaded. You need to download the file. It's there. All the delivered lectures are there. So you can look into that. So new poll has been created for attendance purpose. You need to respond to that poll for attendance purpose. Because sometimes I figure out the numbers are not as many as the participants are there. Maybe some of the people are not aware of that. So those CRs are requested to guide them how to mark their attendance. All right, so we move on to the very last lecture, very short, but going to be comprehensive because things are more challenging behind the scene. We are not interested to go through with all those certain criterions. Rather, we are trying to take glimpse of idea. They are going to be utilized, systems of linear differential equations, but they're not as often being utilized as those first order or second order differential equations. So, but anyway, we will take a glimpse of idea behind the scene. Once we have a system of linear differential equations, how do we simplify them? What are the options behind this? So take a look. So far, what we have discussed. We discussed about the solutions of linear differential equations having one dependent and one independent variable. Whatever the order of the equation is there, whatever the form of the coefficients are there, whether homogeneous, non-homogeneous. Nevertheless, we discussed a differential equation with one dependent and one independent variable everywhere. So in many cases, we come across linear differential equations having two or more than two dependent variables and one independent variable. So this is a broader version. In the previous case, we discussed a differential equation, regardless the order, the form, one dependent and one independent variable. But now we are going to take into consideration the case when we have more than one dependent variables. And eventually they are going to constitute a system. Such differential equations constitute a system of simultaneous linear differential equations. The complete solutions of such kind of systems can only be obtained if the number of differential equations is equal to the number of dependent variables. It is pretty much analogous to the idea that the number of unknowns should be identical to the number of algebraic equations so that we can find a unique solution. So same is the case. The complete solution of a system of differential equation can be obtained if the number of differential equations in that system is equal to the number of dependent variables. So take an idea about a system involving two variables, x and y being dependent, and one variable, t, as an independent variable. So now we have a system involving two dependent variables, x and y, and t is going to be independent variable. then the simplest system of differential equations is the system of two first-order linear differential equations in two unknowns, x and y, and has the form. What the form is, so it is going to be of this nature. dx upon dt a11 x plus a12 y plus function of t. So from here, from the fraction, the one in the numerator is going to be dependent, the one in the denominator is going to be independent variable. So you see x is dependent, t is independent, but if you look into the second, y is dependent and t is independent, expression is there. So x and y are going to be dependent variables and t is going to be independent. So if you combine together, it will take you to the system of differential equations will be having at least two of the equations. So if you combine at least two of the equations, it is going to constitute a system rather than single equation. This could also be written as, for simplicity, for more compact and composed form, what we do, we replace d upon dt as capital D. What capital D is here is an operator stand for d upon dt. Previously, we assumed d upon dx as capital D. So over here in the system, capital D stands for d upon dt. So you need to highlight this one. So dx to the left hand side, a11x to the right hand side. So by taking x common, so it will turn out to be something like that. Take this term to the left hand side and f1 of t to the right hand side. From the second one, take this term to the left hand side with a negative sign and dy and a2 to y, combine them. So it will be of this form. So this system would also be expressed in that particular way. It's the same thing, where all the coefficients a11, 12, 21, and 22 are constants. So again, pretty much the same idea as for one single equation. If the right hand side f1 of t, f2 of t are 0, then the above system is going to be homogeneous. Otherwise, this system is to be non-homogeneous. To solve the above system of differential equations, sometimes it is more convenient to eliminate one of the dependent variable, either x or y, and then from the resulting equation, we can solve for the second variable, and then the value of the resulting variable can easily be obtained. So the idea is that we will try to eliminate one of the dependent variable by playing around with the coefficients, balance the coefficients, and subtract or add one of the equation to the other one, so that we can easily eliminate one of the dependent variable. Once this thing happens, we will be having single dependent variable equation as a result of that. If you eliminate x, so then the resultant will be single dependent variable y equation, and from there we can easily find the solution. So idea is that we need to eliminate one of the dependent variable, and from the resulting expression we will find one of the unknown, and then by backward substitution we will find the value for the other variable. So we have two, x and y. So once you eliminate one of them, find the other, and go back to the first one to find the value of the first dependent variable. Take an idea. Solve the following system of differential equations: dx upon dt, dy upon dt. Now you see that it's a system because of combination of more than one equations. How many dependent and independent variables are there? From this fraction, x is dependent, t is independent. From that expression, y is dependent, t is independent. So overall, we see that we will be having two dependent variables, x and y, and one independent variable, t. So dx upon dt is equal to y. So what we do, initially, we write it down, the given system of differential equations, in the form of capital D. So this one is to be expressed as capital Dx because d upon dt stands for capital D here. So capital dx is equal to y. Take this y to the other side. So we will be having dx minus y equal to 0. And from the second one, capital dy. Take this minus 4x to the other side, plus 4x. dy minus 4y. By taking y common from the right hand side, we will be having this expression. So now you see that we have two equations, number 24 and 25, involving two dependent variables involving capital D over there. So what the idea is, for system of differential equation, we need to eliminate one of the dependent variable. How we do that? So one of the option is there. We multiply equation number 24 by d minus 4. So yes, if you do multiply it, so we will be having d times d minus 4 x minus d minus 4 times y, and you will be having d minus 4y in that equation number 25. So if you add together, so y is going to be eliminated. So operating d minus 4 times 24, if you multiply equation number 24 by d minus 4 and add it to 25, we will be having this expression. You see that it is free from the dependent variable y. So y is eliminated with this operation. So this is one of the viable options. You could also try to eliminate x as well. Depends upon the suitable option. So we have eliminated y with this operation. Now you see that it is pretty much like the previous case, the starting, when we talk about second order differential equations of homogeneous form. So what we do? By taking x common from the right hand side, write it down in the most elegant form, the compact and composed form, f of d x is equal to 0. What is f of d? D square minus 4d plus 4. Corresponding to this one, the auxiliary equation would be m square minus 4m. Merely, we need to replace d by m. So m square minus 4m plus 4 equal to 0. Look into the corresponding values of m, 2, 2. The roots are real and repeated. And we know how do we write it down the solution if the roots are real and repeated. So this is all the solution is to be expressed. C1 plus C2 T. Remember, T is the independent variable now, and X is the dependent variable because this expression is expressed in X. What is X? X depends upon the values of the variable T. So X is dependent and T is independent for this homogeneous differential equation. So this is how the solution is expressed. Previously, you have seen that the solution was written like y is equal to C1 plus C2x e raised to power 2x because of the value of the root is repeated 2, 2. So C1 plus C2t e raised to power 2t because x is going to be function of the variable t here. Now you see that we have obtained x, one of the dependent variable, based upon the independent variable. We are interested to find the other variable. So now we can go back to either equation number 24 or 25, whatever is convenient. So I would prefer to go with 24. Less work is to be done, less computational work is to be done if you take into consideration 24, because we have to find y. Y would be equal to dx. So if you take y to the other side, so y is equal to dx. What is d? D upon dt. What is x? X has been calculated just now, that one. So it means that y will be equal to the rate of change of x, means the rate of change of this expression with respect to t. Capital D stands for d upon dt. So it's basically the derivative, the rate of change of this expression with respect to t. So you need to differentiate. This could also be written as, this term could also be written as C1 e raised to power 2t. The second term C2t e raised to power 2t. And then look into the derivative. Okay, a couple of terms are there behind the scene. If you take the derivative of this one, so it will turn out to be 2 times C1 e raised to power 2t, that one, by using product formula over there. So it will turn out to be C2 e raised to power 2t plus 2 times C2 t times e raised to power 2t. So it's behind the slide, I mean, because of the space issue on this particular slide. So it's a line over there. Anyway, I will make adjustment to that. The outcome is A. Once you differentiate this one with respect to t, the outcome is that one. So this is all. We will be having the general solution of the given system of ordinary differential equation. X, one of the dependent variable, y, the other dependent variable in terms of t. So the idea is A, again, in the highlights. Idea is A, initially trying to eliminate one of the dependent variable by adjusting the coefficients and applying certain suitable operation behind the scene. Sometimes you have to subtract one of the equation from the other one. So balance the coefficients with alternative sign, add together. You will be having a resulting equation in one of the dependent variable. Once we have that, simplify that one, because it is just like the previous case, the most simplest one, when we have second order linear homogeneous differential equation, because you see that corresponding to this one, we will be having f of dx. So our target is to simplify this one, go down with the auxiliary equation, depends upon the nature of the roots, write down the solution for x. X is the dependent variable. So once we get down one of the dependent variable, we are interested to find the other one because it has two dependent variables, x and y. We need to find them, both of them. So try to utilize the most simplest expression from the given system. So we would prefer in this case equation number 24. From there you can find the value of y by differentiating the expression of x just obtained from here with respect to t. So in this way you will get the other dependent variable. So here you go, the complete solution, x and y dependent variable. So pretty much on the same lines, you can try these examples. You see that in the first case we have two equations, system of two equations. Dependent variables are 2, x and y. So number of dependent variables are equal to the number of equations. And then little bit more demanding in comparison of the previous cases. We have 3 dependent variables now, x, y, and z now. X, y, z, 3 dependent variables, system of 3 equations are there, 1 independent variable t is there. You need to play around with that. So that's it. We have tried our level best.